Hello, friend. My name's Derek Harder, and in our video today, we're going to be turning our attention to a new topic. We're going to be looking at generative deep learning. Okay, so this is kind of a hot topic right now, and my goal through this unit, through this video, and the next couple of ones is just to so that you get an understanding of of the building blocks, so you can really understand how generative AI works, right? You really, if you've been following this course up to this point, you have most of the tools that you need in order to understand kind of what's going on here. So, in general, generative AI is a technology that's based on deep neural networks. And in particular, some of the stuff that we've been talking about for sequence-to-sequence learning in our previous unit. So encoder, decoders, transformers, word embedding spaces. Those are all important concepts to understand how generative AI actually works. Okay, so I'm a little bit of a skeptic, as you may know, about the current hype for generative AI. I do think it's useful. I think that it's better to think of generative AI, the way it will come down, as being useful as a way to augment humans' intelligence. Okay, so it can help you, make you more productive. I believe these systems, to help you kind of get things generated, boilerplate stuff like that. But the current wave of that we've seen of kind of hype for generative AI is being oversold, in my opinion. You would think that that it's really on the edge of what we would think of as strong, of what people call strong AI or artificial general intelligence. And it's not that. Okay, so these generative models really are able to capture the latent space of human language, like the English language, and they show the power of being able to do that. But they really are still just doing the same kinds of stuff that you've learned that neural networks can do. Okay, but anyway, so in our video today, we're going to start with sequence generation in order to generate text. Okay, so this is really kind of the basics of how something like a chat GPT or some text generative AI works. All right, are you ready? So let's go ahead and get started. Okay, so how do you generate sequence data? So in this example, we're going to be looking at generating text, and this is really basically what ChatGPT and other generative systems that are generating text do, although they're trained with huge corpuses, so they show kind of the power of having a real huge corpus to build the latent space of the language. Okay, but these techniques are not limited to just textual data. I mean, we could generate actual spoken speech, so they're used for generating realistic speech. You can generate like music. So our assignment, we're going to be trying to generate improvisational kind of jazz using these techniques. So how do you do it? So really, to train a model, and usually we're going to use recurrent layers or a transformer. And we don't need the full encoder decoder because there's really only one sequence. So when we talk about generating sequence to sequence here, the sequence that we're doing is we're taking the sequence and we're training it to generate. So we take the sequence like 1 to n, and we train the model to predict the nth plus 1 token. Okay. So, for example, we already did this when we first looked at sequences for the weather data for the prediction, but we did it slightly differently there. So we would create sequences, and we would chop out sequences and then train it to predict 24 hours ahead. But we could have done it where we, did exactly what we're going to do here, where we trained it to always predict, the sequence up to a particular point. And then make a prediction 24 hours ahead, but then we just move it one time step forward and keep doing that, right? So that's the same thing that we would do here to generate text, right? So we would first train a model like this figure here, you're already familiar with these concepts when we talked about this in our previous unit. So any network that can model the probabilities of the next token, so when we're talking about modeling the probabilities of the next token given the previous n tokens, is called a language model. Or I guess more generically, I would call that like a token model, because we could be modeling the structure of jazz music or of classical music, or we could be modeling the structure of English spoken speech, that kind of thing, right? So we have a token model. So these models, language models, capture the latent space of a language. Okay, it's statistical structure. So for text generation, we already did this as well when we did the transformer, when we did the encoder decoder previously. So the basic idea for generating text is, once you train a model like this, basically you seed it with some starting initial text, have it predict the next one, and then you append that to the end, and you just keep iterating that. Okay, so this is a form of sampling. Here, when we predict the next word, we ask it to give us a probability distribution of what the next likely word is in the text. So as you'll see for generating text here, our next slide, we don't necessarily, to get generative text that feels natural, we don't necessarily want to pick the most highly probable next token in the sequence. So we will do we will pick at random, but using the probability distribution. So we'll be more likely to pick high probability tokens, but we still might pick less probable tokens. Okay, so we do some sort of a sampling method to pick the next word, and then we keep iterating that. Okay, so then we would feed the cat stat on the mat in, have it pick the next token after that, and do that until we are satisfied that we've generated enough text. All right, so that's the basic idea of what our text generation works, right? Just keep sampling using some sampling method, add that generated output to the end, and feed that into the model again to get the next token. So good generative methods for generating text or generating other kinds of sequences need to use some sort of a sampling strategy. Okay, so the naive method would be greedy sampling. Okay, so remember that the result from a language model, like we've described, is going to be a softmax probability distribution over all the potential tokens. So you could always just pick the one that has the highest predicted probability of being the next token in the sequence given the n previous tokens, right? So that's called greedy sampling. But the problem with greedy sampling, where you're always choosing the most likely next token, is if you do this and you try that out, you'll see that it very quickly results in generated text that's highly repetitive and predictable. It doesn't feel like natural language or a natural sequence at all, right? So what needs to be done usually for good generative methods is some sort of random or stochastic sampling. So again, remember that the result from the output is going to be a softmax probability distribution over the tokens. So instead of picking the one with the highest probability to be the next token, you sample usually weighted by the probability. So you are most likely to predict the token that had the highest probability, but with some probability you'll pick a token that's not the highest probability, the second or third highest probable token in the sequence. Okay, so this is useful. To do this successfully, we need to have something like this method on the right-hand side. So it's useful to control the amount of randomness in the sampling process. So we'll refer to that as the temperature. So in optimization methods, there's often this temperature parameter that controls the amount of probability that's done in the sampling here. Let's show this actually in working in practice here. So let's look at how this sort of reweighting of the distribution works for your sampling strategy for generating a sequence. So the textbook doesn't describe this very well. So basically temperature, if temperature is 1, you'll get the same distribution as you input. So a temperature of 1 doesn't change the distribution at all. And you'll be sampling using the original probability distribution of space. Because you're dividing by 1, nothing happens here. So temperatures that are close to 0 or 0 result in greedy sampling. So if you use a temperature of 0, you'll basically always be picking the most probable token as the next one that you will use in the generative process. But temperatures greater than 1 will make it so that you're more likely to pick other tokens than the one that was most probable. Okay, so for example, if we have our original distribution that looks like this, the distribution, this is a softmax distribution, or it's a correct probability distribution, so it has to sum up to 1, right? So this is meant to be similar to the distribution that our textbook showed for this example. So here, a better illustration is trying some different temperatures from close to 0, around 1 here, up to temperatures that are greater than 1, right? So when it's 1, you get the original distribution, right? So in this distribution, the token 1 here, so this is token 0, 1, up to token 9. We've got 10 tokens in our vocabulary. Token 1 was the most probable. It had almost a 25%, 23% probability, right? So a temperature of 1 doesn't change the distribution. Temperature of 0 just changes it into greedy. So in this case, we will always pick token 1, and there's little to no probability. If we make it 0, there would be exactly no probability of picking any other token than the most probable. But if you have temperatures that are greater than 1, the higher the temperature, the closer it gets to being just a random or a uniform choice, right? So with a high temperature like 10, I mean, token 1 is still the highest, and token 9 is the second highest, but everything has a much higher chance of being selected here, right? So your sampling strategy, so if your temperature is too high, the text is just going to be gibberish. But if it's too low, it'll seem repetitive and boring. Okay, so usually you have to kind of tune this, and there's no like a loss function, individual one. So usually tuning this comes down to a judgment call of the people using the generator of what temperature works best to get the most useful natural sounding sequences out of your generator. Okay, so and finally, let's give just a quick example of generating text. So we're going to return to the movie review database, the sentiment analysis, so positive and negative. So you might already have this data. If not, you can re-download it. If you remember, the way we did it before, we'd added in some code that actually randomly selected some of the reviews out of the test to make a validation test set. Although it doesn't matter. If you deleted it and recreate and untart again, originally you'll just get 2 subdirectories, test and train. But we don't need the labels. So when we're doing text generation, we're going to create a model using the sequence to sequence, where the input sequence is the 1 to nth token, and we try to predict the nth plus 1 token. Okay. So so either way, if you set the label mode to none, basically if you create one of the Keras text data set from directory data sets, it will find every .txt file in the subdirectory structure and use all these. So in this case, we're going to be using all of the text files in the negative and positive directories that it finds under the ACL IMDb directory here. And in this case, when we're generating the text, we really don't want it. We didn't remark on it before, there were some HTML tags, this break tag in there. We really don't want our text generator generating non-human text in this example. So we'll go ahead and replace all those with just blank spaces to get rid of them. All right. So, I can't remember, but there's a large number of text in here. So let all these load. Let's go ahead and let them load. Okay, so once that finishes loading, double check, but you should get over 100,000 files, just over. As a reminder, so our data set at this point is just going to be returning, since we don't have labels, is just returning tensors, but of raw strings here. So we have stuff like this, although we are, mapping out that one particular HTML tag that they all had. Okay? So, we have to do our usual step. We need a vectorization. In this case, we're just going to we're not going to specify for the normalization. So we'll end up using everything to lowercase, removing all standard punctuation. We want to encode this using integer indexes for vocabulary. We'll keep the 15,000 most frequent words in the vocabulary, and we will limit just using the first 100 words of all the reviews. So similar to stuff we've done before in using this IMDb data set, right? And then finally, we need to actually, separate this apart so we have the data to train with and the labels, right? But in this case, we're not doing a binary classification in our sentiment analysis. So we don't have like a 0-1 binary label. So this is a sequence to sequence task. So basically the input for training is the sequence up to the nth token. And then the target is going to be the token, the next token after that, right? So this will do that. So remember, so I'll come back to that. So we're going to be using the transformer and the positional encoding that we did from the previous unit. So if you're following along in this notebook, those were actually loaded before here. So just some reminders. So in our network here, we're going to use an embedding space again, or use that positional embedding. So remember that creates two embeddings. It creates the word embeddings for these the integer indexes in a vocabulary, but it turns these transformers into kind of hybrid. So both sort of things like recurrent layers that have positional information, but that take the whole input as kind of a flattened sequence, right? So the positional embedding gives us sort of the best of both worlds for things like a transformer decoder. So we get two embeddings, the word embedding, but also the position embedding. And then the output from that, though, we go into a final dense layer that takes it back into our original vocabulary size of 1,500 words. So the result from this dense layer is a softmax over the whole 15,000 word vocabulary that we kept for our vectorization here. Right? So, and I meant to mention also, so again, back to this, what we're actually training is for the model to predict the nth plus one word from the sequence 0 up to n, right? So, if we're using this transformer with positional encoding, we are using that causal masking. So remember that. So it does the right thing while it's training. When it's trying to predict the nth plus one word, it won't look at the whole sequence in the transformer decoder layer. It'll only look at the sequence up to 0 to n using this causal masking. Okay, so we're using kind of all those tricks that we discussed before here in our model. Right? So let's look at the summary of that real quickly. All right, just to make certain that you understand. All right, our final dense layer is outputting a softmax over to 15,000. We've got an embedding dimension of 256 coming out of this positional embedding, right? So although it's actually got two separate embeddings here, the position and the word embeddings. And internally, our transformer decoder is using a large number, but it will come out again as a 256 embedding, which the dense layer reconverts back into the 1,500 indexes of our original integer vocabulary. Okay. So while we're training this, we could ask for example, the accuracy on predicting the next token. That would give you a little bit of idea what's doing. But here in our example, instead we'll add a callback that will actually generate sequences using different temperature values. So in this case, we'll pass it in with temperatures from 0.2 up to 1.5. So a little bit before and after 1. using this method here to sample the next one and generate strings. And we will just always prompt it with an initial 2 words, this movie, and ask it to generate a movie review where we give a movie review. What was it? The generate length here. Here, but so the generate length of 50 here. So only half the size of what we're training with. But this callback is just we need a way to evaluate the model. In this case, it's a lot more subjective than what we've done before. So we can't really look at our loss or like a metric like accuracy. So this will give us a better kind of feel for how the generation is doing at different temperatures for every epoch here. Okay. So let's go ahead and try it out. This will take some time, and I'll probably have to stop this before we do a full 200 epochs here. But let's go ahead and start our model fitting here. So if you run this, this is kind of what you'll see. This is after just one epoch of training here with the different temperatures, the result that we got from the generation. All right, so like if we look at the 1.0 temperature, it's using the probability distribution that comes directly out of the model. And you can see, some sense, right, even after one generation of training here. So, I'll only be able to let this run for maybe 10 epochs. So on my system with a GPU, an epoch takes about it takes a minute or two to train one epoch here. Oh yeah, it took about 2 minutes for me for the first epoch to finish training here. So we got the second epoch coming out here, and we're generating again at different temperatures. Some examples of movie reviews. Yeah, I'll let it run for a bit here, but I'll probably have to stop after 10 or 20 epochs here so we can finish up the discussion. So if you have time, you can maybe let it run overnight to see how it does for 100 or 200 epochs of training. One warning, sometimes it does get stuck. So you'll get it even with high temperatures of it just repeating itself. That can happen, and you can maybe, if it happens consistently with you, maybe you need to change some of the parameters, or maybe use an additional multiple layers of transformers or some things like that can help you always get repetitive output after 100 epochs or so. Okay, so after about 10 epochs of training, probably won't be too good. And like I said, sometimes, unfortunately, you can get into loops. It's looking quite a bit repetitive on this particular run. I don't know if it'll get out of that or not. So assuming that you can wait long enough, you probably need at least more than 100 epochs or so, and you get into a particular location in your search space where it's not kind of stuck, you can get some good sounding stuff, sound reasonably, like correct grammar and things, usually at a temperature a little bit lower than 1, like the author says. So yeah, this kind of generation of text is about having lots of computational time and really big data sets, right? So by training a bigger model, so ChatGPT is really kind of similar to this, but it's going to be many layers of transformers like this, and corpuses that cover almost the entire internet that they've gathered. So yeah, a deep stack of transformers. But if you have those kinds of computational resources, you can get the sort of performance that you see on like a ChatGPT or similar model that are popular nowadays. But yeah, kind of my own caveat: don't expect it to ever generate meaningful text other than kind of by random chance, even for these really large generative models. You are just sampling data from a statistical language model of the latent space of the language, right? So, these models are all form and no substance. They seem impressive, but they're really just doing this sampling on this latent space. All right, so that's it for this unit where we looked at text generation. So just a couple of things to remember. You can generate discrete sequence data by training a model to predict the next token. And that is basically what these generative AI models are doing, right? So you're familiar with kind of the basics of how they work. In the case of text, we would call that a language model. So it can be either done word by word or character by character generation. And it works by, building up a statistical representation of the latent space of the language that it's trained on. You do have to be careful about your sampling method. Sampling the next token requires a balance between adhering to what the model judges most likely, but introducing in a little bit of randomness so you get more realistic results. One way to handle that is, for example, a temperature, like the softmax temperature function that we introduced. So that will allow you to tweak the amount of randomness you want on your generative end when using a generative model. So, and like I said, don't expect these to generate meaningful text, right? So language models are all form and no substance. They really are generating from a statistical model of the language that they learned on. Okay, so I hope that was a useful video and that you better understand now kind of the basics of how generating sequences and generating text works. And I hope you'll stick with me for our next video, where we'll start looking at generating image